Year 13, Chapter 19, Force and Motion, Lesson 2, Resolving Forces. Now, so far in Year 12, you've only looked at forces which are horizontal or vertical, making it very easy to find resultant force horizontally and find resultant force vertically. We're now going to look at forces which act in different directions, and we're going to look at a technique called resolving forces into components. This relates directly back to the work on vectors that you have been doing. So let's start with an example. Here's my force, and it is a force of magnitude 12 newtons. As you can see, it is acting at an angle above the horizontal. Now, I need that information about the angle in order to proceed, so I'm going to fill it in. The angle here is going to be 60 degrees. Now, what we do is we resolve this force into a pair of components. Think about vectors. If I start with a vector from here that goes along horizontally like that, and then I add another vector, this time going up vertically from here like that, then we know that the vector sum of the blue and the purple components will equal the 12 Newton force. We know that. We know that if we have a horizontal vector like that, A, and we add a vertical vector like that, B, then if we go from the start of vector A to the end of vector B, this vector here is the resultant of A and B. It is A plus B. We're doing the opposite of that. It's like we're taking the resultant vector here, and this is our 12 Newton force here, and we're splitting it up or breaking it down into its individual components. I'm going to call these components X and Y, and we're going to use some very basic Key Stage 3 level trigonometry to find out what they are. So I know that cos 60 is the adjacent X over the hypotenuse 12, which means I can rearrange this to give me X equals 12 cos 60. I know that sine 60 is equal to Y over 12, and I can rearrange this to give me Y equals 12 sine 60, and we can work those out in a second. So my 12 Newton force, which is a vector of 12 newtons, can be written in the format of these two components. If I wanted to, I could write them in the form of a column vector. So I've got my 12 cos 60, which is my horizontal component, and my 12 sine 60, which is my vertical component. So if this green highlighted force, which has a magnitude of 12 newtons, if I call that vector F, then that is equal to this column vector here. Must underline it so it's clear that F is a vector force. So let's see if we can do that again with another example. So here's my force. Look at the direction of the arrow because that's very important. And the force is of magnitude 8 newtons. Let's now draw in the components. I'm going to go from the start of the force like that, horizontally, to get a horizontal component. And then I'm going to go up vertically like that to the end of the force like that. So I get a vertical component as well. We'll call them X and Y. And you can see in both cases, we create a right angle triangle of forces. I need to know the angle before I can proceed. So I'm going to call that 30 degrees over here. And let's label the force, the 8 Newton force, as F again, so we can see. Now, using a bit of trigonometry, we know that cos 30 is equal to X over 8, the adjacent over the hypotenuse. So X is equal to 8 cos 30. Again, we can evaluate that as needed with a calculator. And we know that Y is part of sine because it's the opposite. So if I use sine 30, I get the opposite Y over the hypotenuse 8. So that gives me Y equals 8 sine 30. Now, we can then evaluate these if we want to. Cos 30 is root 3 over 2, so that gives me 4 root 3. Sine 30 is a half, so the y value is 4 newtons. So I can say that F is equal to, in the format of a vector. Now, look at the directions here. That's really, really crucial that we observe this. X goes left, okay? Unlike X in the first example, which went to the right. Y goes up. Remember when you learnt about I and J components? That's the positive direction in the horizontal direction. That's the vertical direction, which is positive like that. Now, in the first question, it was a bit easier because we were going with a component to the right and a component upwards like that. In this question, we're going with a component to the left and then a component upwards to create our force F. The component to the left is going in the negative I direction like that, so it's a negative component. So our I component is minus 4 root 3. Our vertical component, however, is upwards, which is still positive, so it's F. Now, one thing we can do is work out the magnitude of F. You'll recall how to do that. You take the I component and you square it. You add on the J component, all squared, and then you square root this result here. Pythagoras theorem, essentially. So if we work that out, that is 48, which is the 4 root 3, plus 16, square rooted, which gives us the square root of 64, which gives us 8 newtons. So you can see that that is the magnitude, 8 newtons over here. Let's try another example. Each time it's the direction of the force as well as the magnitude that matters. So it's the angle and the direction of the arrow that really makes a difference here. So here's my force. It's got a magnitude of 6 newtons acting in this direction, and it's an angle of 45 degrees below the horizontal, going in a clockwise direction like that. Let's draw in some components. Hopefully you can see that there's a horizontal component going to the right like that, and then there's a vertical component going down like that. Now I'll call my horizontal component X, I'll call my vertical component Y. Now remember positive directions. The positive I direction is to the right, the positive J direction is upwards like that. So we can use trigonometry again to work out our components. We know that cos 45 is equal to the adjacent x over 6. So x is equal to 6 cos 45, which actually works out to be 3 root 2. Sine 45 is equal to y over 6. So y is equal to 6 times sine 45, which is 3 root 2. So my force F, which has magnitude 6 newtons, so all we know about F is its magnitude is 6 newtons. We can write F out as a column vector. Now its I component, nice and easy, goes in this direction to the right, so it's in the positive I direction, so that is simply 3 root 2. But its J component acts downwards, its vertical component is like that, so it's going in this direction here, in the negative J direction. So we need to fill that in as negative 3 root 2. Now if you want to, you can also write this in component form. So I could write that F is equal to 3 root 2 in the I direction minus 3 root 2 in the J direction. You've seen that before. You've seen how to express vectors in a line format, in a column format, and in components I and J. And that's what we're doing here. We're resolving a force into its horizontal and vertical components, into its I and J components. Let's try another example. So we have a force which is going to be 12 newtons, and it's in this direction. It's an angle here of 40 newtons. Now, let's draw in components. So starting at the beginning of the 12 Newton force, there's a horizontal component like that, and then there's a vertical component down like that. Let's call the horizontal component X again, the vertical component Y again, and look at the directions of them. You should now have a good idea of the fact that we need to observe direction. The horizontal component is going left, the vertical component is going down. Both components need to be listed as negative when we write F out in the format of a vector. So cos 40 is equal to adjacent X over the hypotenuse 12. So that tells me X is equal to 12 cos 40. Sine 40 is equal to the opposite, Y over the hypotenuse 12, which gives us Y equals 12 sine 40. But remember, the directions of the components matter. So F is equal to negative 12 cos 40 as its I component, and negative 12 sine 40 as its J component. We could work those out and round them to their decimal values as well. Now, what I would like to do is then generalise this, because we can do this much more quickly than having to resort to some of that more basic trigonometry each time we do one of these calculations to resolve a force or split a force into its components. So I want us to start with a force like this. We'll have it in this direction, but actually we can use this and apply this in multiple directions. You will see that in just a moment in an example. And we will call this force vector F. And what we will say is that the magnitude of vector F is just F, like that. Now, this force here is going to be split up into a horizontal component like this, which we'll call X, and it's going to be split into then a vertical component like that, which we'll call Y. So really important that we see that there is a right angle triangle that we're working with here. We'll call the angle theta. Okay. Now, at the moment, I've drawn this so the X value is in the positive I direction and the Y value is in the positive J direction. Let's apply a bit of that basic trigonometry again. Cos theta is equal to the adjacent X over the hypotenuse F. So remember to use the magnitude here, not the vector form of F. So we can rearrange that so X is equal to F cos theta. Sine theta is equal to Y over F. So rearranging that, Y is equal to F sine theta. And that's what we should try and aim to do each time without using these steps here. We need to aim to get ourselves into a position where we can just say X is equal to F cos theta and Y is equal to F sine theta. So we avoid that middle step of writing out cos theta equals X over F, etc. Now, F can now be written in its column format. So its I component is F cos theta, its J component is F sine theta. So we can write it as F cos theta I plus F sine theta J. Now the idea is you simply look at the hypotenuse, which is the magnitude of your force, F. You look at the horizontal component and you ascertain whether it's going to be adjacent to or opposite from the hypotenuse. That one's adjacent, so it's simply F cos theta, and I should be able to get to a stage where I can straight away say that X is equal to F cos theta, and you can see that because X is adjacent to that angle there. I then look at the vertical component and I can see that that's opposite the angle, so it's a sine component, so I need to get to the stage where I can say that Y equals F sine theta straight away. The idea being that you aim to try and miss out these steps here and you go straight to your resolved force into its components. Let's see if we can do this in an example. So I'm going to start with a particle which is going to be acted on by a series of forces. Look at the angle and the direction of each force as well as its magnitude. So the dotted lines represent axes so that we can see the direction of the forces more easily. I'm going to take I as being in the positive horizontal direction, J as being in the positive vertical direction. We don't have to do that. As long as I and J are mutually perpendicular to each other, we can rotate this pair of axes, but for the moment we're going to stick with them in these directions. Now, here are the forces that we have acting. I have force F1, which acts on the particle in this direction here. And the arrowhead is like that, so that's force F1 in a vector form, and it is 60 degrees, like that. And the magnitude of F1, I'll write it along the side here, is 15 newtons. So I know that the magnitude of F1 equals 15 newtons. Now F2 acts vertically upwards on the particle like that. So that is force F2, and I'll write its magnitude next to it. It's 8 newtons. So mod F2 equals 8 newtons. Now, force F3 looks like that. Remember, these are vector forces, so we write them as vectors underlined. Its angle is 48 degrees here, and it's a magnitude of 7 newtons. So mod F3 equals 7 newtons. Now, I then have force F4, which is down in this direction here. And it is an angle of 76 degrees and it is 6 newtons. So mod F4 is equal to 6 newtons. Now, what's left? We've got force F5, which is going to be in this direction over here. And that is of magnitude 12 newtons, and the angle there is going to be 30 degrees. Now, our job is to resolve each of these forces into its components and then find the resultant force. Now, the resultant force, which we'll call sigma F, so we're finding the vector sum of the forces, is force 1 plus force 2 plus force 3 plus force 4 plus force 5. But you can't just add the magnitudes of the forces together. We've got to add them together in their horizontal and their vertical components. So let's start with force F1. I'm going to write out a pair of brackets there. Now you can see that its magnitude is 15 newtons. It's got a component like that in the horizontal x direction, positive, and a component like that in the vertical direction, like that. So it looks like that. And then the angle, of course, is 60 degrees here. So the x component is a cos component here, so it's 15 cos 60. I know it is positive because it's going to the right. So the I component is 15 cos 60. The j component is vertically upwards. It's where I've labelled it with a y. It's opposite, so it's a sine component. It's opposite the 60-degree angle, so it's a sine component. So that is 50 sine 60. Now, F2, that is simply 8 newtons acting vertically. So there is 0 I component. So F2 has 0 I component and it's got 8 newtons acting vertically like that. Now, F3 looks like that. So it's got a component like that, a horizontal component like that, and a vertical component upwards like that. Its angle is 46 degrees. So, first of all, let's label its magnitude, which is 7 newtons. This component here is a cos component as it's adjacent to the 46-degree angle, so it's 7 cos 46. This component here is vertical, upwards, so it's 7 sine 46. Sine because it's opposite the angle 46 degrees. Now, directions, the cos component, the I component is negative, it's going to the left, so it's negative 7 cos 46. The j component, vertically upwards, so it's 7 sine 46. Let's now look at F4. F4 is in this direction like that, it's 6 newtons. It's got a component, horizontal component like that, so that's going to be negative, and downwards on the y component as well, so they're both going to be negative. The angle is 76 degrees, so this component here is adjacent to the angle, so it's 6 cos 76. This component here is opposite the angle, so it's 6 sine 76. So this gives me vector for force 4 as negative 6 cos 76, and its j component is negative 6 sine 76. We've got one left, which is force F5. Let's take a look at that. Now, force F5 is down like that, 12 newtons. It's got a component going to the right like that, and then a component going down like that. So let's look at the angle, 30 degrees. Look at the horizontal component, the I component, it's going to the right, and it's adjacent to the angle. So it's 12 cos 30, it's positive, it's going to the right. The j component, downwards like that, is opposite the angle 30 degrees, so it's a sine component, so it's simply 12 sine 30. So I can then create an overall vector for the resultant force by adding together the individual I components and then the individual j components. Make sure your calculator is in degrees. So we need to do 15 cos 60 plus 0 plus negative 7 cos 46 plus negative 6 cos 76 plus 12 cos 30. And I'm going to get a decimal value, 11.5781 ... I'm going to store that in a calculator memory. Then for the vertical components, 15 sine 60 plus 8 plus 7 sine 46 plus negative 6 sine 76 plus 12 sine 30. So the j component is 26.2039 ... So if I want to find the magnitude of the resultant force, I take these two values, these two components, square them, add them together, and then square root. So using Pythagoras theorem, this gives me a magnitude of 28.64 newtons, 28.6 newtons to one decimal place. And I might also want to draw my resultant force. So let's look at those components again. It's got an I component of 11.57, so that means it's got a component in the horizontal direction, like that. And it's got a j component, which is 26.39. So that means it's got an upwards component like that. And we can draw in the resultant force like that, which of course is sigma F. So really interesting to see that when you add together those 5 forces and look at the overall effect of them, you get a force in this direction. If I want to, I can then calculate my angle here, theta, using trigonometry. So I need to do arc tan of 26.2 ... divided by 11.578. And that gives me an angle of 66.161, 66.2 degrees to one decimal place.